Okay, good morning. Today's speaker is Xing Wang from University of Rome 3, and he will speak about electroweak physics and in general Electroweak-fit at the muon collider. Quick thing for this afternoon, I remind you that for those of you that want to come, we have this event at Galileo's villa at 3. So we will probably organize some self-organized groups to work up together. Maybe I will send an email to all of you later with the details, and maybe we can also set up a time at which we meet together. Okay, please.
Right. Perfect. Okay. Hi, everyone. My name is Xing Wang. Currently, I'm a postdoc at the University of Rome 3. So it's really nice to come to Florence. So this is also my first time being here. It's really a nice town to visit here. So in this talk, I will be talking about the electroweak scattering processes at the future muon collider, and also the electroweak global fit for muon collider we're currently working on. So this this is the paper that we'll push out soon. And also at the end of this talk, I will also discuss some aspects about the electroweak PDF, because we certainly had a lot of discussion during last week, but most of them are focusing on the standard model aspect. So basically at the end of this talk, I will be commenting on about applying the electroweak the effective W approximation to BSM processes. Okay, so this is just the content of my talk. So first, I will give you a little bit motivation and also lay out the setup for SMAFT. And then I will mostly focusing on discussing the VBF processes at the muon collider as a mean to probe the BSM effect. And then towards the end of this talk, I will discuss some of the caveats or say the lessons we learned for applying the effective W approximation to BSM processes. And in the end, I will conclude. Okay, so we have heard plenty of discussion and last week and this week that there are really kind of a lot of new physics we can do at the muon collider, and in particular, the muon collider is really a collider of electroweak vector bosons. So by going to 10 TeV center mass energy, we basically can produce a lot of vector boson fusion or vector boson scattering. And so for the standard model processes, the VBF production pretty much dominates for all different kinds of final state production. And this is due to the fact of this logarithmic enhancement caused by the collinear splitting of the W boson. And in contrast, for the any S-channel mu annihilation processes, it's at least in the standard model, it's basically surprised by this 1/s S-channel propagators. But of course, I'm here to talk about the BSM physics at higher energies. So as we have already heard some discussion from Alfredo's talk this week, that standard model EFT has been been a very useful framework to study indirect effects from BSM. So assuming there is some heavy new physics that would manifest at low energy in terms of those higher dimension effective operators. And in particular, at dimension 6, by just a simple dimension analysis, we can immediately write down the scattering amplitude that has very different scalings. For example, at dimension 6, where you always have a lambda square in the denominator. However, in the numerator, you can either have v squared, the vacuum expectation value, or the linearly depends on the energy or energy square. And of course, if the energy is high enough, such that the energy is much larger than the VAV, then at the high energy muon collider, the dominant effect will actually come from this e square over lambda square term. So that the leading kind of generically speaking, the leading BSM effect comes from the interference of this energy square term interfering with the standard model amplitude here. And of course, so using this formula, you can quickly estimate what kind of sensitivity we can have, right? So roughly speaking, if we expect this 1 over square root of n would just be the statistical uncertainty that we will get. And then if by equating this to this E square BSM effect, we can basically derive the sensitivity on this cutoff scale lambda here. So here, basically, if you roughly speaking, you have 1 femtobar cross section with 10 inverse femtobar luminosity at the muon collider, then you basically can probe the cutoff scale to 10 times the energy of your scattering. So, yeah. Yeah. Sorry. Yeah. Sorry. Yeah. Absolutely. It should be 10 inverse attobar here. Sure. So of course we have heard from Alfredo's talk yesterday that if you consider any kind of mu annihilation processes where you maximally utilize all the collision energy, then this scattering energy here will be basically of order 10 TeV, right? So which means you can directly probe the cutoff scale up to 100 TeV. That has been very well discussed in yesterday's talk. But of course, here we want to study the VBF processes. Now, the immediate question we would ask is, for the VBF process, how high energy can we actually probe? So of course, on one hand, if you only look at the hard scattering, yes, there are BSM effect that grows with energy, actually energy square. But on the other hand, if you look at the parton luminosity of those gauge bosons, they on the other hand decreases with energy. So basically, in the end, it's really a competition of these two. Okay, so then to basically estimate what kind of sensitivity we can have, we can just adopt this very simple formula, the effective W approximation, that gives some very kind of intuitive idea of what kind of energy we can probe, right? So generically for signal, right, typically we expect the energy growing effect, in our signal mostly come from the scattering of longitudinally polarized W bosons, right? So here I am plugging the kind of PDF for the longitudinal W bosons, which has this very simple scaling behavior here. And on the other hand, for the background, which is a standard model, here I'm just be very kind of hand wavy. You can just assume it could be, mostly longitudinal vector boson scattering or transverse. Let's try both. So here, this FT is just the PDF for the transverse polarized vector bosons, which has this behavior here with logarithmic dependence here. And again, just again, so for the standard model, we just assume it's a constant. The overall normalization at this point, I don't really care, so I just put number 1 here. And then for the BSM effect, again, it's we are more interested in the contribution that quadratically depends on the scattering energy. So it goes as S hat over lambda square. Here, S hat is the minus 10s of your partonic hard scattering. Right, so just to use this very kind of naive, also simple formalism, you can make the plot here, right? So here are the x-axis is the square root of S hat, basically the energy of your hard scattering, and then y-axis is roughly speaking S over square root of B. Of course, here in this plot, the normalization is completely arbitrary. The absolute magnitude of the red curve and the blue curve are it doesn't really mean anything here. So the normalization is really arbitrary. But here we just want to see the energy dependence of those of the sensitivity S over square root of B here. Okay, so now let's first talk about the right curves, right? So the right curve, the assumption about the right curve is simple, that the BSM is really dominated by, again, the longitudinal vector boson scattering, and then the standard model is, mostly transverse. For example, this standard model background could be, gamma fusion kind of thing. So that is mostly transfer. And then you can already see the best sensitivity only comes from around 2 TeV in terms of the partonic center mass energy. And then the other case is, again, we still assume the BSM come from longitudinal scattering, and also the standard model, in this case, also come from the longitudinal scattering. So then in this case, you can see the kind of optimal bin lies around 3 to 4 TeV. So therefore, from this very simple, kind of naive estimation, we can already see that by going into this, vector boson scattering processes, of course, we cannot fully make use of the whole 10 TeV collider energy, and the best sensitivity usually comes from the energy scale around the 3 to 4 TeV there. So therefore, in that sense, the VBF process in general has, relatively speaking, weaker sensitivity in comparison to annihilation processes. Simply because here you don't make use of all the energy available here. But of course, on the other hand, the VBF processes also have their own kind of usefulness. For example, you can use them to probe that the BSM effect that are not directly accessible through the annihilation process. For example, the annihilation process always come with some interaction directly related to muon. So if you have interaction that does not have muon participate in, and then you can rely on the VBF processes to probe those effects. And also the VBF is different processes from annihilation, so therefore it also kind of can have the potential to give you some complementarity if there is any kind of flat direction in your BSM effects. And of course, so generically speaking, right? So here I'm just trying to categorize all the simplest, I would say, VBF process into kind of 3 categories, right? So the first one is, of course, Higgs production, which I will be mostly focusing on in this talk. And then you can also study the scattering of VV to a pair of fermions. And in particular here, we focus on the case where this fermion can be either quark, light or heavy, or electron or tau. Here I skipped the muon because in case of the muon, you can directly reverse this hard scattering process and directly probe those kind of operators through the diboson production from mu plus to mu minus. And of course, in the end, you can also study the vector boson scattering, where final state you can have W or Z, or in principle, you can also have Higgs here to have different combination. But here I have already singled out the double Higgs production because it's this process in particular has its own importance here. Okay, so now let's get into the first category, which is the double Higgs production. Of course, the most important thing I think about these double Higgs processes at the muon collider is that this channel offers us an opportunity for measurement of the Higgs self-coupling. So this is something that, for example, FCCE or CPC that cannot really compete in terms of Higgs self-coupling. There, you can only measure the self-coupling through some loop indirect effect. But here we can, because of the enough center mass energy, we can directly produce the Higgs pair. And of course, we want to stick to this SMAFT framework. And then at the dimension 6, these are the common operators that would modify the double Higgs production here. And of course, here I'm only focusing on the CP even operators. There are a bunch of a few others that are CP odd, which are not included here. So of course, for this double Higgs production, we can make use of the differential distributions in order to not only to suppress the standard model background, but also to distinguish between the effect of different operators. For example, in this analysis in particular, we use two kinematical variables. One is the Higgs pair invariant mass, and then the other one is the transverse momentum of the final state Higgs. The thing I want to say here is that basically you can make use of different observables. For example, here I show the distribution plot of the Higgs polar angle in its center mass frame. And then the lower panels are for the Higgs pair invariant mass distribution. So basically, as you can see, the different, of course, in the plot here, we use the different bases than the SMAFT. But nevertheless, you can see the different distributions for different for different operators that you can basically make use of this kinematical information to disentangle different operators here. Yes. Mm-hmm. Yes. Yes. Mm-hmm. Right. Okay. So like yeah, sorry. So for the distribution I showed here, they I don't think we plotted the self-coupling in this plot. So all of the colored lines are the BSM the BSM operators that are related to the interaction between gauge boson and Higgs. So the Higgs self-coupling are not plotted in this plot. Except for the coupling that's related to two Higgs. Yes. Yes, I think so, right? So if you have the FCCE measurement before, then yes, you can make use of the FCCE to measure all the BSM operators that related to, for example, single Higgs production, right? Yes. Yes, yes, that's right. So basically, all the other 5 operators, they have certain energy growing behavior, but the OH itself it doesn't. It always goes as v square over lambda square. But however, nevertheless, we include this operator because it's just too important to not to include. Yes. Okay. Yeah, and of course, in order to be able to tell, the effect from different operator, one crucial question we want to ask is, okay, can we actually distinguish between WW fusion and ZZ fusion, right? Because both processes can give you Higgs productions. So ideally, if we can observe the final state of muon, yeah, no problem, because after all, they are very different processes. They have very different final state. But however, identifying the final state of muon may not be that easy. For example, in the left plot here, I show you for the double Higgs production, the theta angle, the polar angle of the outgoing muons. And for different energies, 3, 10, and 30 TeV colliding energy. So basically, as you can see, as you go to higher and higher energy from green, red to blue, the outgoing muon is more and more forward along the beam direction. So therefore, if due to some limitation of our detectors, which we have heard a lot in the past weeks about those nozzles, you don't really have a great coverage along the forward direction. So therefore, you have to have some very large. By large, I really mean compared to the detector at the LC in terms of the polar angle. So that's where the second plot is, where the x-axis is the cut on the polar angle. So basically, as you can see, if you can only if the detector only have the coverage from say 10 degree to 170 degree, which correspond to 10-degree cut here, as you can see, you actually lose a lot of cross-section in terms of ZZ fusion here. For example, in particular for the 10 TeV, roughly speaking, you would lose 1 or 2 order of magnitude cross-section. So therefore, we have to. So we really have to try better with the muon collider detector. So one thing that has been proposed is to have certain forward muon tagging. So this is about angular. Here I've written it in terms of rapidity. The coverage up to rapidity of 6. So of course, for this forward muon tagging here, we really don't care much about the precision on the measurement of its for momentum. But in this case in particular, we really care about whether there's muon or not. It's really a yes or no question, or not how many. So therefore, this is the plot I show here. So again, here I'm plotting the cross-section that satisfy this tagging criteria, eta, less than certain cut, which is the x-axis here. So again, for different color from green to blue, it goes from the 3 TeV to 30 TeV colliding energy. So of course, because here we are discussing the ZZ fusion, right? It comes from the muon emitting a kind of a collinear Z boson, and immediately we know the PT of the outgoing muon will be, roughly speaking, of order mz. right? So then you can basically convert this PT of order empty into rapidity, which goes to, for example, rapidity of around 5 for a 10 TeV muon collider. Which means if we can really achieve a forward muon tagging of a rapidity less than 5 or 6, you can really kind of keep most of the cross section from the ZZ fusion. Yes. So here it's really just a straight cut. Okay, yeah. So yeah. So for example, this is the cross section as function of this data cut. As you can see, for the 10 TeV, the turning point is basically around 5 TeV ish. So basically, as long as you can tag, about go beyond eta around 5, say 6, then you basically keep all of the cross section of the ZZ fusion here. Yes. Okay. So therefore, this forward muon tagging is really helpful for us to distinguish between the WW fusion and ZZ fusion. And here, of course, this is just the detail of the analysis what we did. So for the Higgs channel, we basically just study the simplest decay topology where Higgs decay to jet. Here you can include both BB bar, CC bar, and also even glue, which in total counts about 70% of the branching fraction. And of course, there are just some basic acceptance cut for the jet. And for the Higgs reconstruction, here we just took a very simple assumption that the overall reconstruction is around 30%, which is in line with the efficiency people have been using for IRC and etc. And of course, one thing we want to do for sure is to make use of this forward muon tagging. So basically for the Higgs pair production, you can basically categorize all the events into 2 categories. One is that no muon at all being tagged. And then the other case is the at least 1 muon being tagged. So then the second category would be from ZZ fusion. Yes. So for here, all we need is just to tell yes, there's a muon, or no, there's no muon. Because in this forward region, the muon has to basically go through the nozzle, right? So the resolution won't be great. But of course, how much experimentalists can do, it's something interesting to study. But for here, at least for the Higgs production, we don't care. We just want to know yes or no, there's a muon or not. Hmm. From sorry, what? Okay. Okay. So here is the kind of preliminary SMAP fit we got, and in particular, this come from the Higgs pair production. So basically, in particular, the first 2 operators are related to the modification of the Higgs self-coupling. And so in the end, so the estimation for the muon collider is that for the self-coupling, you can basically reach the precision of 3 to 5%, which is directly comparable to the projection, for example, at the 100 TeV PP. Yes. Yes. So Yeah, okay, so I think that there are other operators, but yes, in this plot, it's a global fit with 12 operators. So for the muon color input, in this case, I think it's just Higgs pair production. So we for this plot, we did not put in other constraints, for example, from diboson final state, etc. Yes. Yes. So sorry. So for the Higgs production, we basically do a two-dimensional binning in terms of the Higgs pair invariant mass and also PT of the Higgs. Yeah. That I'm not sure. Yeah, I have to double check.
I'm pretty sure that single X collider measurements are inside. I can open the. No, it's not. And what's the reason to do the block? I think.
If I don't have what? No. So in terms of Higgs Higgs self-coupling, it doesn't really matter, right? So the muon tagging here only matters if you want to tell apart the W from Z.
What do you need it? What is the effect of distinguishing W and Z in terms of effective operators?
For that, well, I don't think I have a plot here to show that yet. Yes, I think so, but yeah. Yes.
That way you can see that kappa W versus kappa W not just with the vertical SU2 basically comes back to kappa to the direction. But given the ratio to cross section, these plots will be on tagging without muon tagging there. And on top of which one thing no one ever doesn't do things like that kappa W versus kappa T, the T parameter really also doesn't happen. But then if you the T parameter, then it's for precision. Yeah, but if you have like T, then simple. So you're saying that the like yeah, I mean typically what these Higgs fits, those are not also included, or at least I don't know if you do it on top of fork one versus not having fork one. There is one combination that box and the operator that can.
Okay, so next, okay, so I want to also briefly, yes.
Here you put the complete standard model background. Or what do you do with the background with this double X? Four jets plus
no, so the background would just be the standard model Higgs pair production we used here.
You only did Higgs pair production?
Yes.
Okay. You didn't put the ZH or the ZZ production?
So
Ironically
No, so in this analysis we did not. So but that basically depends on how well you can separate your Z-peak from Higgs-peak.
Because you will have a reasonably large fraction of the Z that you identify as a Higgs.
Well,
The section is much bigger.
sure. So basically, there are two things you can explore here. So one is just the digest environment mass distribution, right? What kind of resolution you expect that from the detector, and then the other one you can use is, for example, B tagging. That will, but
Those groups that did the full bit studies on the Higgs, and then we did full background specifically. Yeah, I know. Yeah, I mean, I think the statement is like, if you do a more sensitive statistical analysis versus like having a better pH discrimination, like we came up with kind of the same numbers, even though in ours we could discriminate Z and H based on having kind of a better assumption. Their detector model is worse, mix them more, so. Just to repeat the question here. Only future to more.
yes. That's right. Sorry,
I think not putting the background at all, I think is a very optimistic assessment.
no, it's to Z.
I think this is taken from our paper, by the way, Dario.
We put the background.
No, we did put a selection. So we did set an efficiency selection that reduces the signal, because we judged that with that efficiency we would get rid of,
Yes.
for example, the background. Remember what?
Yeah, no, but we put the background.
We did estimate the background, but at the end we didn't include it because we say that we think that we can capture with an efficiency on the signal of what we set to be 30% or whatever it was, such that then the background would have been negligible. We estimated the background, but we didn't put the background. And I think we should have included the background. We should. Yes. So, but this is your fault.
And I think there's at least 2 or 3 groups that are actively doing that.
Yeah. But I say the logic is that this background is not overwhelming a priori. It can be.
Yeah, so in any case, so in this analysis, we didn't really do a detailed analysis for Higgs reconstruction. Instead, we just apply this reconstruction efficiency, assuming that most of those effects will come into this number here. So then the next thing I want to briefly talk about is the other processes, which is VV to FF. So again, the F here represents either quarks or electron and tau. So these are the operators that would contribute at order E square over lambda square to these processes. And of course, like I said, the muon for muons, it can be best probed by just looking at the diboson production directly from mu here. And of course, there's one more operator that's is too important to not include. That is the modification to the top Yukawa coupling. So this operator in particular does not go with the energy square, but instead it's linearly in terms of energy. But nevertheless, it's something important to study at the muon collider. right? So I think one of the biggest difference between the Higgs HH final state versus FF final state is that for the FF final state, there is a very huge standard model background from gamma fusion. Right, so for example, this is the PDF of different partons. As you can see, the photon content is much larger than the W content here. So then again, the question is, okay, so we talk about forward muon tagging. So can forward muon tagging help here? Well, not so much, right? For example, you can roughly estimate, right, if you have 3 TeV outgoing muon, which goes up to rapidity of 6, which translates basically the PT of this muon only around 15 GeV-ish. So which means below 15 GeV in PT, you cannot really distinguish between the W fusion and photon fusion here. So, and of course, you can try to make use of the overall PT distribution here. So, for example, this is the this is the probability of splitting in terms of the transverse momentum distribution. And again, so in this plot, I am using arbitrary normalization. So photons should be much larger, but here I just normalize it down so that it looks kind of nicer in one plot here. So basically, as you can see, for different splitting, they have very different behavior. So for photon, we all know that it's infrared singular here. So it goes all the way up as you decrease the transverse momentum. But however, for the massive gauge boson, they have a cutoff coming from its, say 90 GeV mass. And also there is a subtle difference also between the splitting of transverse vector boson and longitudinal vector boson. So basically the longitudinal tend to be softer, more collinear in compared to the transverse in compared to transverse W, for example. So in this plot, as you can see, the very low PT is really dominated by the photon distribution, and in this intermediate region, around 50 GeV, that's where the longitudinal W reaches maximum. So this is also where most of the BSM effects come from. They come from longitudinal vector boson scattering. So therefore, basically, and of course, to distinguish this W versus photon, of course, we don't. If the muon is below 50 GeV, we can't really distinguish it from a neutrino. But nevertheless, we can measure the PT of the FF bar system. That's something we observe, and then we use this PT spectrum to distinguish from the different initial bosons here. So for example, in this particular analysis, we did 3D binning. So one is, of course, the invariant mass of this FF pair. And then the second variable we use is the transverse momentum of the FF system. And then the last is just the polar angle of the fermion in its center mass frame. And so basically the global fit is still ongoing. But I can show you some of the preliminary kind of result that to show the distribution here. So for example, this in this grade, the x-axis is the PT of the BB bar system. So in this particular case, we consider FF to BB. And then the y-axis is different bins for the BB invariant mass. And so for each kind of box, it's color coded and also represented by the number here is the 1 sigma statistical bound in terms of the cutoff scale if you only use this one bin alone. So as you can see, the most sensitive the most sensitive bin come from the region where you have very large MQQ environment mass, and also the PT of the QQ bar system is around 100 GeV-ish. And in this particular plot for the BB bar, just from this one single bin, you can already probe the lambda up to this is 9 to 10 GeV. So if you combine all the bins here, you can go beyond 10 TeV for sure for this BB bar system.
The end is like the gamma gamma bag is not that bad because even if you do even in the low PT bin, you have 8.6.
Right. Yeah, I mean, it depends, right? So it depends on your final state. So for BB bar, it's 1 nice surprise. Surprised by the charge, electric charge, right? If you have up-type quark, then yeah, it would be more severe contamination from the gamma-gamma fusion here. So sorry. Yes. Yes, in principle, you could also get a very strong bond from the precision measurement. So yeah, so here I'm just showing the potential of the muon collider. So in the end, once all these results come into the global fit, that's where we will see the comparison.
I mean, we think with respect to lab, we believe there is a significant, there is a problem with respect to lab, but not with respect to
Yes, BB is the final state here. The what? Oh yeah, so here as you can see the binning we start from 150 GeV, so we don't really go down to the pole, either Higgs pole or Z pole, W pole, whatever. Yes. I think it will be. My impression is smaller than that.
Do you have
No, I do.
I think the normalization is that's the normalization without any other factor, right?
No, yeah, you're right. That. Mm-hmm. Right. So in principle you should, but of course here the QCD induced say glue scattering, they would typically come with a much slower kind of scale. Yes.
They come from
Well, yeah, it's a PT dependent statement. Yes. Well, so I think so here we have the lowest value we had here is 150, right? So if you divide by 2, you're still looking at 60 GeV-ish jet. So for that I'm not sure. Well, I mean, at best, I think the QCD would be only comparable to gamma-gamma fusion, if not smaller. Okay. Right. So, well, I mean, yeah, like you said, it doesn't really matter here because, you know, the glue kind of fusion process will have a very similar kinematics of the photon scattering, right? So then once you perform analysis, the optimal point will always try to stay away from wherever the photon matter most. Yes. Yes. Okay, I only have one slide about the VV to VV because this is still progress. But in any the case here, we have all these different operators that would be also by constrained by the VV final state. So this, I apologize that I don't really have any result to show. The only thing I can say is that so. This is actually turns out to be quite challenging to compute in unitary gauge, where there are very huge gauge cancellations happening here. So it's quite challenging for event generators to actually have a reasonable and stable result here. So before I conclude, so I also want to briefly discuss the application of the effective W approximation or WPDF in general, together with the study of the BSM physics. So basically, so we had a lot of discussion during last week, mostly about EWA in the standard model. So the effective W approximation is usually a very useful approximation to help us to get some intuitive insights into the physics we are studying. For example, in all the previous slides, I have tried to use the EWA a few times to get some kind of naive but also intuitive estimation of the physics there. It's also known that as long as you can apply a proper cut, that in many cases the EWA can also serve as a reasonable approximation, also quantitatively. But of course, that's for standard model, and for the BSM case, there are some extra cares you have to beware if you want to apply the EWA approximation to the BSM effect. So this is basically something we learned during our study of the double Higgs production. So I think this kind of diagram appears in the discussion last week. So basically, so if you consider a process where you have mu to nu and WW, right? So we know that this process cannot be very well characterized by the effective W approximation. And the reason is kind of easy to tell if you just draw all the Feynman diagram and look at their topology. And in particular, so these two diagrams are two of all the diagrams that contribute to this process. And by looking at the topology here, you can immediately see that the left plot can, of course, well captured by the effective W approximation, right? Because here you have two T-channel W propagator here. On the other hand, for these processes, right, you also have WW in the final state, but however, the tip channel propagator here, it changes. Instead, you have a neutrino propagator here. So therefore, just by staring at those Feynman diagram, you can immediately tell, okay, so this is, of course, yes. Yes, yes, if you can apply a proper kinematical cut, right? For example, here the W will be, the W at the top will prefer to be collinear to the initial W's, right? So yes, I totally agree that if you can apply proper kinematical cut, yes, you can single out, you can surprise this diagram here. So this is the story of the standard model, because there's not that many complicated fancy interactions happening there. But however, once you try to apply this EWA to BSM, sometimes it also happens that even if the Feynman diagram have a topology like this, the EWA could still fail. The reason is because inside this blob, you can have very different tensor structures here. So for example, this is one of the case that we studied. So of course, this is one particular dimension 6 operator, but of course, in this paper, we had basically composite Higgs in mind. So it uses a slightly different basis than Walther basis. But nevertheless, if you consider a dimension 6 operator like this, right, then by just drawing all the Feynman diagram, this operator would only contribute inside this blob. So whatever Feynman diagram you draw, the Feynman diagram will always have these two W propagator. Yes. Yes, yeah, exactly. That's what I was going to talk about. Yes. So basically, it's not very manifest using this basis. However, you can apply the equation of motion for W boson. Then immediately you can actually write this operator in terms of these operators. So now you see there is a kind of a contact interaction involving Fermi comes up, which means upon using the equation for motion, this diagram would become contributions that looks like this. So then obviously this diagram, these two diagrams cannot be captured by EW very well. So that's so therefore the EWA you cannot use EWA to quantitatively study the effect of this operator. So here all the point I was trying to make is that sometimes by just simply staring at the Feynman diagram here may not be really telling us what's going on or to those T-channel W propagator. So that's one example. So I also want to make another example. So this is for different operators, and the EWA is not a good approximation to study this operator for a very different reason. So this is the reason we studied, and in particular, so basically to have this effective W approximation work, we have to stick to the collinear approximation, right? So then, yeah, basically for the scattering amplitude, you can expand this amplitude in terms of PT. And then, so once you compute the cross-section, you convolute this hard scattering amplitude with PDF, and then integrate over the azimuthal angle phi. Then many of the interference term will drop. And so basically, in the end, all the interference term either vanish once you integrate over phi, or they are energy suppressed. For example, here in this formula, I have 4 terms. So the first 3 terms are the terms that captured by the effective W approximation. And then the 4th term here, it doesn't vanish upon integration over the azimuthal angle phi, but nevertheless, it's energy suppressed. It has this factor MW over E. So that it's suppressed at higher energy. But however, so now let's see the effect of this C6H. So in this table, I show you in the high energy limit the leading behavior for different operators. So basically, as you can see, for the operator C6H, the high energy leading effect actually come from the helicity plus minus 0, which grows linearly in terms of energy. So now, if I want to interfere this with the standard model effect, right? So I can either interfere with the standard model amplitude with the same helicity, but it's 1/E suppressed. Or I can interfere with the standard model contribution, which goes as constant, but with a very different helicity, helicity combination. So therefore, which means this subleading term will not be necessarily suppressed, because now the BSM effect will have introduced some actual energy growing behavior, which would potentially spoil the power counting that you use in deriving the effective W approximation. So here it comes my conclusion. So here I mostly discuss the probing the BSM effect through the vector boson fusion processes, and even though for the VBF processes we don't fully utilize all the 10 TeV colliding energy, but we can still use it to provide useful sensitivity bound on BSM effects coming from certain operators. And of course, in the end, I also briefly discussed that the effective W approximation, while it's a really powerful tool for us to understand the physics intuitively, in many cases, it may not be well suited for describing certain BSM effects. Thank you.
Nobody? We already had a lot of discussion, so we can also. Yes.
Yeah, thanks for the very good comments on this thing. However, in the Feynman diagram, in the left-hand side, where you already gave the green light. And what kinematic cut you prefer to do for the the T-channel photon diagram for the protonic cross section? It's WW to WW, and you have to put an angular cut, a PT cut. Otherwise, it's just divergent.
Sorry. Yes. You're talking about the
one in the left.
Yeah. So, well, you can't, right? So because in practical, right, the effective W approximation, which just give you this unphysical pole that somehow you have to regulate. But yeah, I guess that's one of the shortcomings of using EWA, that sometimes it will introduce some artificial, unphysical poles. So I think the diagram he was talking about is this one, right? So you have a W, but a T-channel photon. Right. So in this case, if you use EWA by putting this W on shell, right, you introduce a T-channel singularity here. But in the actual process, the W never comes on shell. So this T-channel pole is not physical.
Gamma to WW.
Sure.
So that's another diagram with the effective gamma approximation.
Yes.
Maybe you should draw that as well.
Sure. So, okay, let's just do it again. So you have
Just gamma, yeah.
gamma. Yes, yes,
It's
yes,
the same
yes. But
diagram, except it's the
yeah,
symbols changed.
yeah, I just want to draw a different one in case
Yeah,
that you want to keep
Is
both.
this one actually larger than the one that you drew?
Yes, it will be.
Yeah.
Yes, yes, yes. So I'm not trying to say which one is the leading effect, but just by simply applying the EWA, you're introducing something unphysical here.
Yeah, but if the W is always off, oh, this is what you were saying. If the W is always
Yes,
off
yes,
shape,
exactly, exactly,
then
exactly.
that means you can't reach.
Yes.
Okay, that's fine.
Last week that approximation is not about approximating diagrams. It's about approximating in certain kinematic configuration. And of course, if the W goes straight, where you get hit at singularity, is a region where you knew already that there is no way to make the effective W approximation. There is no logic for doing that. So it's part of the approximation. These Ws have to have large PT. Otherwise, you know that you cannot factorize hard versus soft. So it's a corollary if you want, but yeah, a corollary of. Yeah, because if PT over MW, actually the PT of the W is not large in comparison with the MW and with the kappa T of the radiation, there is no way to apply the approximation. This approximation does not make, there is no, is an approximation, is not a good approximation. There are power corrections. Yeah. So yeah. In particular, if they have too forward, this means that PT is 0 and then the approximation is not supposed to work.
Yes, yeah, yeah. So I think I totally agree that as long as you can apply the proper kinematic cuts, you can always make the EWA work. But on the other hand, in practical, that's a more complicated question where certain cuts where you can really achieve certain cuts because there are once you get a neutrino involved, sometimes you just cannot guarantee you're always in the kinematic region where the WW scattering is the leading effect.
Can you go back to the slide, please, where you had the partial waves for the different helicities? So for which process did you actually calculate this? This is
this is the WW to Higgs.
So this is only WW to Higgs.
Yes.
Because if you do the same thing for the WW to WW, then you again have to take into account
right, yeah, yes.
the region around the beam to take it out from the calculation.
Yes.
I was curious, have you guys, obviously the operators that grow with energy are giving you the power here, but if you think of integrating models out at tree level and looking at the models that generate energy growth operators, so going back to the study on Z primes yesterday, how well do the models versus the energy growth operators agree? Like for at the LHC, the EFT only really agrees if the Z prime is strongly coupled. And so you're really, from the EFT perspective, you're only really caring about strongly coupled physics. But can you bound weakly coupled physics, but that's just above the energy scale very well? I mean, does the EFT picture kind of agree decently well? Or it depends upon your luminosity that you guys are doing, but you're already assuming a big luminosity. So I was curious, have you done the comparison?
Well, so far not yet. So basically, well, one thing you can already more or less see is just from what kind of sensitivity you can get here. So of course, I kind of cheated a little bit. I'm showing you the best channel, kind of best result we got in all the among all different channel, different operator. So in this case, like, as you can see, for single cell, you can get around 10 TV. You know, you can imagine if you combine all of them, you're probably 14, 15 TV-ish. But of course, there are other operators that other channels you cannot even reach, say, 10 TeV, the muon collider energy. So for that, for those bound to make sense, it has to actually come from some strongly coupled the physics.
So then for anything that generates these, you should probably have a much better bound for looking for simplified models at the muon collider.
Yes, I'm showing the best.
But I'm just saying you put a weak coupling in there and it's below 10 TeV. Yeah. 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 So that's what I'm saying. For weakly coupled physics, you'd do better from searches. Yeah.
Yes.
Well, but you can put in them one and ask whether you're getting, because the problem for the LHC, right, is that in the region you're doing, then you typically have a large width for your model once you get to 1 or larger, and then your expansion parameter in G over M is the wrong expansion. And you don't have an EFT that's systematic any longer.
But I mean, the cutoff doesn't need to be 10 TeV, right? Given that you plot MQQ, you can, yeah. Yes. No, but even no, if you bound MQQ to 1.5 TeV, you already get a bound on 7.5 on the scale, which gives you a coupling of what, 3, 4. Sorry, 1/4, 1 over, yeah, 1 over, yeah. Okay, thanks again.